Okay, let's have a look at some of these problems. If we go to the course site, it's here. And this is very small. Let's make it bigger. Okay. So you can get the complete text here. These videos are introductory, not so complete. You do have answers to odd-numbered problems. You can also get the answers to the complete problems under the instructor's manual, and this is available to everyone. All right, so let's take a look at our sections, which is 2.1 through 2.4. Okay, so first we have the definition of derivative. I wish I could get this gone. Maybe I do this way. There we go. All right. So the idea of derivative as a kind of slope. Let's see if he has a picture here. People often have a picture. I don't really see a picture here. Oh, here we go. Well, here you have your delta t and your delta f. So delta f over delta t should be very close to the slope. Delta f is the same as f of t plus delta t minus f of t. And delta t is delta t. So that's where we get this equation here. So I'm sure you've seen this before. And you're taking the limit. You're taking delta t smaller and smaller. So this is an instantaneous speed. It's a tangent line. It's a slope. All of those things are the same thing. Sometimes instead of delta t, they use h. You might have f of t plus h minus f of t divided by h. Same thing, same idea. All right, so that's the basic intuitive idea of derivative. And it's a very powerful idea. You take the limit. So, for instance, if you get x over x, the limit of that is 1. Okay, so well, we're using the variable t. All right, so we have limits. Now, I'm not going to spend a lot of time calculating these limits. I'm going to do more with application. All right, so here they do this kind of stuff. You take this and you take the limit. When delta t becomes small, then you get minus 1 over t squared. Basically, if delta t becomes small and it's not canceling another delta t, then you replace it with 0. All right, so that's kind of the idea. And I'm not going to go into the rigorous proofs, just understanding that on an intuitive level. All right, so increasing is positive slope, so that means derivative is positive. Decreasing means negative slope. Derivative is negative. A maximum or minimum has derivative 0. I think you should remember that from your calculus class. Adding to a function doesn't change the slope. It only shifts the entire, only change the entire function. But if you add 1 to the slope, it becomes more steep. All right, so let's see. All right, let's see. Think about this. All right, so this is all intuition. Okay. These kinds of things we don't need to look at right now. So that's 2.1. And then let's look at 2.2. Powers and polynomials. So here you talk about derivatives of polynomials. Here he's replaced the dt with a h. And he's doing a standard computation of a derivative. Right? We're taking the cubic function. If you know what the cubic function looks like, it's like a parabola, only even more curved. So you can draw that yourself, what a cubic function looks like. But you can see, if you think about what a cubic function is, it does certainly have a positive slope. And when the function is 0, when x is 0, then the slope is 0. So it's always positive and 0 at 0. So that kind of reminds you of a parabola with vertex at 0. And in fact, that's what it turns out to be. So you can do this calculation. My delta f is f of x plus h minus f of x. So you computed that here. Then when you divide by h, the h's cancel. Some of them cancel, and then the remaining h's go to 0. Right, so this is a calculation. I'm quite sure you've seen this before. And you get 3 times x squared. General formula for a polynomial. is right here. Derivative of x to the n is n times x to the n minus 1. All right. One way you can remember this is that the derivative has a lower order than the original. Right? You reduce the order by 1. And so the n knocks down to n minus 1, but the n goes out front. So don't confuse the formula for derivative with the formula for integral. Derivative is slope. The order goes down. Integral is area. The order goes up. But integral is for something for later. All right. So you have these calculations here. He talks about Pascal's triangles. So derivative of polynomials, basically you have a sum of monomial terms, a sum of powers of x times constants, and you take the derivative of each one separately. General rules for derivatives: if you take the derivative of a function times c, then you multiply the derivative also by z. And the derivative of the sum of functions is the sum of derivatives. Right? So if we go to some... All right. So we use derivatives to create differential equations. So we have a derivative term within the equation, and that becomes a differential equation. And in fact, this is where it all started. Well, the reason why Newton even invented derivatives is he wanted to solve differential equations. F equals ma, if you remember physics, that's actually a differential equation because a is a second derivative of the position. Right? So here we have this. All right, so let's go back. Here he's actually talking about indefinite integral. I'm sure you've seen this before also. So what he's saying is that the solution of this differential equation is not a unique function. In fact, since the derivative does not change when the function is shifted, then the solution also has an arbitrary shift in the y direction. It has an arbitrary plus c. And the way you check this, of course, is you take the derivative of this function and you end up with 3x squared. Right? So you kind of reason your way backwards. All right? So simple differential equations is just basically reasoning your way backwards. All right, then he starts talking about economics. Now this is one place where derivatives play an extremely important role. And in one area there is an important role is this idea of marginal cost and marginal income. Here he gives some good examples. He says the average cost of making automobiles may be $10,000, but this includes the cost of setting up the factory, of hiring people, and so on. So making one more car will not cost an additional $10,000 because this average cost includes the fixed costs of capital and startup. All right. If you wanted to think about that, we could draw let me just draw the line here. Okay, so here if we have the number of cars here, and here if we have the total cost, so this is the total cost per number of cars. All right, even to make 0 cars, you have a factory cost. So you're going to have some factory cost. And then the more cars you make, you're going to have a straight line. All right. So I think it's clear from this picture the average cost and marginal cost. The average cost here, see if I have 1,000 cars, okay, and then this might be 100,000 up here. Now remember, this 100,000 also includes this plus this amount. All right, so it includes the total. So the average cost is the 1,000 over 100,000. Okay, so that is the slope of this line, but we don't really interpret it that way. The way we would interpret average cost is it's the height of a rectangle whose height is kind of the average of these heights. So this is average cost. All right, now marginal cost would be the slope here. If I make one additional car, how much more does that cost? And this slope is going to be not as steep as this because this red is actually the same as the slope here. Right? The red is the ratio of the total cost to the total cars, and that's just this slope of this line here. But the marginal cost is here. So the marginal cost I can write here. Okay, so that's the difference between average cost and marginal cost. Let's go back here and see what else we have. All right, for those of you who are working, he also gives another very good example. Your average pay and marginal pay. All right, if your regular wage is $10 an hour, and then you have overtime of $15 an hour, then if you're into overtime, your marginal wage is $15 an hour. But your average wage will not be $15 an hour because your wage includes both your 40-hour-a-week wage plus your overtime wage. All right? So there's a clear difference there between marginal wage and average wage. All right, so let's consider costs. And he's thinking of this example, cost of producing X tons of steel. If I produce an additional delta X, then the total cost is going to be y of x plus delta x. The extra cost is delta y divided by delta x. That gives the average cost per extra ton. As this delta x becomes smaller and smaller, you get dy dx, which is the marginal cost. So here if we have a function where the cost, the cost function is here, it's this parabola here. So it's an increasing cost function. The slope is it's not just increasing, but the slope is increasing at an increasing rate. So the marginal cost, if the cost is x squared, marginal cost is 2x. Okay, so that's going up very rapidly. This is called diminishing returns to scale, basically. If you have more and more quantity, the cost goes up even faster. So your returns are going to be diminishing. It becomes more and more expensive to produce additional amounts, basically. Okay. All right, here he makes the point that in economics you're interested in relative change, not absolute change. That's what you do in economics. You see what happens if you change the conditions, how is that going to change the economy? If I change the price, how is that going to change my sales? How is that going to change my profit? If you know anything about economics, they usually have supply and demand curves. Supply means how much the supplier is willing to supply given the good is a certain price. And certainly that's going to go up as price goes up, because the more something costs, the more people will want to supply. On the other hand, you also have demand. So demand will go down as the price goes up, because people will want less. And these two interact. For instance, when COVID came out, you have masks. The demand for masks suddenly went way up. You still have the supply. When demand went up, then this demand curve shifted up, and the equilibrium point came here. The price was higher, and consumption was higher. Now, as COVID lasted, the mask producers started producing more. Production costs went down, so the supply curve went down. Okay, as the supply curve went down, the demand might have been constant, but as the supply curve went down, the demand also, the point of equilibrium moved as well. Let me just show that quickly here. Here we have supply, here we have price, and here we have quantity. Okay, and here's my original supply and demand curve. So supply might be like this. This is supply. And then demand may be like this. Okay. All right. So when COVID started, this demand curve shifted up here. So that's COVID starts. Okay. All right. But then what happened after some time is that the supply curve went down like this. I'm sorry, the supply curve went up. People were willing to supply more at lower price. So the supply curve went up like this. Okay, so the price went down. So when COVID started, it started here and it moved steadily this direction. So masks are now not as expensive as they used to be. Of course, this doesn't take into account the idea that the supply might run out. This model does not take that into account. All right. All right, so let's look at how economics deals with relative change. So for instance, we can talk about relative change in price and relative change in demand. So that would be concerned with the demand curve, and that's what you call elasticity of demand. So it says if the price goes up by what percent, then what happens? Then the demand goes up by 1%. Now remember, the percentage is given by a ratio of the change divided by the amount. All right. So this on top here is the relative change of demand, and this is the relative change of price. And as I said before, to get a percentage, you could multiply both of these by 100, and of course the hundreds cancel. So this elasticity is also elasticity of percentage. All right. So that's how you can understand elasticity. You can also have elasticity of you can have elasticity of demand. You can also have elasticity of supply. So the lower the elasticity, the less sensitive the quantity is to the price. So for instance, if I have an elasticity of 0, that's a flat curve. No matter what the price is, the demand is the same. If I have a elasticity that's very high, then then you can see that the relative slope is very, very, very high. Now they had a picture here. I don't know where it went. I did see a picture. There we go. So this is very high elasticity. Okay, so this one says elasticity equals infinity. So if you go, if you increase the price just a little bit here, then the supply goes up, jumps up suddenly. All right. So that means you have, what did I say? If you increase the price just a little bit, then the supply goes up suddenly. So that would be a case where elasticity of supply is infinite. On the other hand, if you had elasticity of demand is infinite, that would mean as the price goes up, there's a price where suddenly the demand goes down to 0. Right? So that would be elasticity of demand is minus infinity. All right? So you can have the same idea both for supply and demand. All right? So you can use these ideas to do some of the problems. You can see how that can be used in a practical example here. Demand is an increasing function of income. Okay, so instead of price, we can also think about income. Income determines how you spend your money. The more income you have, the more you're going to spend typically. The more income, the more demand. So you can have different goods that have different elasticity. A luxury good is going to have elasticity greater than 1, where it says doubling your income more than doubles the demand for caviar. Right? If you make up $1 million, then there's a certain point where caviar becomes something that's easy to buy, and you have more than enough. Now, of course, once you get very high income, that's not going to be true. I mean, you're not going to eat tons of caviar, but at a certain point, you're going to have a elasticity greater than 1. So elasticity can depend, of course, on the income. If something that's a necessity, it's inelastic. So like bread, okay, so, and it's not going to double, okay? So like he says, this gives a way to talk about ideas in economics that are intuitive. Okay, so this is an interesting note on how this supply and demand curve picture depends on the free market. And if you don't have a free market, you can't use that picture. But you can still pose that situation in a calculus way. Right. All right, so here's a question on economic activity, elasticity. You can read this question. Okay, so that's kind of an introduction to the concepts, and we can spend some time doing sample exercises. That's it.